Hi everybody. We're moving on to 8.2. We move on from 8.2, we go to 8.3, and again the title is a bit long: Divide and Conquer Algorithms and Recurrence. And so this is basically an application of recurrence on these guys, but really what we are interested is in the complexity of this type of algorithms. Now, divide and conquer algorithms, we haven't really talked about the term yet, but we have seen some of them. And so I'm going to describe today what actually they are. And then in the next video, I will show you how recurrence can be used to calculate complexity. However, the recurrence relations, as you will see, will be different. But we'll talk about that in a second. I will talk about them already today, but the solving of this thing is going to be something for next lecture. So what are divide and conquer algorithms? Let me try to say it in a few words, and then we'll look at examples where hopefully everything becomes much clearer. The divide and conquer, it kind of refers to principle of the Roman imperial times, from Caesar perhaps brought it into attention, is we should rule our realm, the Romans would say, by dividing and conquering. So what meant was we divide the people that we want to conquer, we put one against the other, we support one and support the other, which people, even in modern international politics, is being done all the time. And then once they weaken themselves out, we conquer. Okay, so that's not really what we want to do. What we're talking about is an algorithm that does the following. It says, okay, I have a problem that I have to solve depending on a certain size, a list of a certain size, a problem of a certain size n. So remember, complexity is always in terms of n, where n is the number that you're dealing with, and in terms of n, where n is the size of the input. I'm a bit imprecise here, we will see when we see examples what we meant here. So n is the size of the input, and what the divide and conquer does is okay, I'm going to subdivide my input into smaller groups of same length, or almost the same length. Say, for instance, I divide it in 5 equal parts, and in each part I'm gonna, each 1/5 of my whole size, I'm dividing it in 5 parts, and each part I'm going to solve it again. Now that makes me have to deal with much smaller size things, right? If I start with something size 10,000 and now I'm going to divide it in parts of 5, then I only have to deal with each problem of size 2,000. And I repeat, because it's a recurrence. So next time I will only have to deal with something of size 400. And the next time only size 80, and the next time something only, 16 or something. So it gets really small after a few recurrence steps, which is not the case, of course, if you do the recurrence by subtracting 1. If you have size, where were we, 10,000? I forget now what I started with, but 10,000, if I go 1 less, then it's 9,999. It's not, and I keep going. After 5 steps, I'm still in the same order of magnitude, right, really. Whereas dividing makes things much smaller very quickly. And so that's going to be the efficiency of these algorithms comes from that. Okay, so so that's the divide part. Now, what's the conquer? Well, of course, you solve the problem for each of the smaller groups, but that solves each of the smaller groups. What about the original group? And that's the conquer. You have to now, the results from each of these 5 sub-problems that you solved, you have to interpret that, what you get from each 5, you have a group of 5, right? And each gives you an answer. And now you have to say, what can I do with these answers? How do I put together the actual solution of my original problem from these smaller sub-problems, the answers from these smaller problems? That's the conquer part, that's the putting together part. Okay, let me give you an example. We have talked about search algorithms. So a search algorithm normally has a list. Let's start from 1, A1, A2, A3. And here the size, I mean the length of that list. It could be numbers, it could be words, it could be more complex data structures. And we have another guy, X, that's of the same type. And the question is, is X, so question, this is what the algorithm tries to do, is X in L or not? That's the question that we want to solve. And we want to be a little bit more precise. So let me give you an example of a search algorithm, what we call the linear search, was basically our first algorithm in discrete math 1. It's very simple. You walk through the list and compare each time with x. And if x is there, at some point you will find it and say, okay, here the number 17 is 17, x actually is equal x. So you can stop at that point and say, okay, I'm going to not only tell you, yes, it's in there, but I'm going to even tell you which one it is. It's the 17th element. Okay. Now, if x is not in there, you go through the whole list, and that requires you to go the whole list. You cannot stop at any point. You're going to have to walk through everything, and then only at the end can conclude, oh, it's not there. In which case, you return answer 0, because that means that's supposed to be meaning to be not in there. That's what we call linear search. And the complexity, if you think about the complexity, as I said, we're going to think about complexity, is very simple, right? It's n steps, so O of n. Okay. Now, there are better, and we have seen this also in discrete math 1, which is called the binary search. And what does the binary search do? It's exactly a divide and conquer algorithm. So that's going to be an example of that divide and conquer algorithm. However, it assumes something quite important, that this is a sorted list. In other words, we have already arranged the list in increasing order of the values of these AIs. So if it's numbers, it's just listed by big order of magnitude. If it's words, it could be alphabetic ordering, and it could be other orderings that we might think of. We'll see about things like that later when we talk about graphs and trees. Okay, so that means that the list had to first be sorted, and we will talk about sorting also. There are also divide and conquer sorting algorithms, but let's do the simplest one first, is the binary search, assuming that we have a sorted list. So I'm going to do this on an example. Let's take the list 1, 3, 5, 6, 9, 10, 11, and 14. I'm going to take a list of a certain size, and I will talk about why. So here the size would be 8, right? But there's a reason I choose 8 and not, for instance, 9 or something like that. Because what the binary search does, it says, okay, guys, what you're going to do is you're going to split it in half. And so now that's exactly what I said, dividing. 2 groups of 4. And what you do now, so I want to okay, this was an example, this was a list. My x, let x be, let's say for now, be 5. Okay, so what do? You divide it by 2 and you do 2 comparisons. You compare your 5 with the biggest element of the smallest group and the smallest element of the biggest group. So those 2 you compare with 5. Okay, 5 is somewhere, it's either so you see here there are 3 possibilities, 6 and 9, we know that they must be less than each other. So your x can be either here, it could be here, or it could be here. Right, the 3 spots that it could be if you think of this as the real line. If you think of this, here is 6 and here is 9. So where could that mystery element x be? Now, if it's here, in other words, if the let's for instance, if I do this with x is 7, okay, so I'll go back to x is 5, but so okay, let me do it in a different color perhaps, so that we keep track of x is 7. So if x is 7, then the answer is here, because 6 is less than 7 is less than 9. What does that mean? We know then that there is not in the list. So I'm yes or no here, so yes or no. So I'm just going to put no in here. Okay? So in other words, if I find myself in between, then I know it cannot be in the list. Okay, in this particular, so this for x is 5, the answer is different, right? For x is 5, let me do that in a different color. X is 5 in green. So in x is 5, we say, okay, 5 is less than 6. So we are in this part here. So we know now that we can restrict our attention to the list, the first list, and we repeat. But what has happened is the list is half the size. Okay, so if we would think about this, what would be the complexity of such an algorithm be? So, okay, yeah, sorry, let me just perhaps been a long time ago. So what would be the next step be? Well, you would divide this smaller list now in two, right? So you divide it in two, and then you're going to compare with these guys. Is it less? Where are we? Are we on this side, or on this side, or in between? Well, we are on this side, right? Because actually we're equal to that. But so you could put this as a small step and say, okay, we can stop already, but perhaps we say, okay, we know that we're on the right hand side, so we do one more step, we divide one more time, so this is now the remaining group that we looked. We divide again, we know now that we are on this part, by the next comparison, right, we compare with 5 and 6, we see we are in the left side now again, and since there is only one element in that left side, it must be that element, and that's it. It is a bit harder to keep track of the position here. So this is more an algorithm that is a yes or no algorithm. Okay, but it is still sometimes it's more than often enough. And with small modifications, you can also keep track of the actual place where it would be. Okay, so that is how this works. So that's as I said, the divide is we divide it in problems of size half. Okay, so we have, so let f of n be the complexity of this binary search for a list of length n. Of length n. Now, okay, what do we realize? Well, first of all, the problem divides the list in two. So we actually are solving the problem now over lists of size n over 2. How many of those lists do we have? Well, we have this list, 1, 2. So we have two lists of that size. You would say, is that not always the case? You will see, sometimes that's not even the case. But so we have two lists of that size. Now, what's the complexity of solving a list of this size, Well, that's just by definition f of that number. Okay, so this is the complexity of these smaller groups, but we have two of them, so we have to do it twice, and then we have to put it together in the sense we're gonna always have to compare with these two endpoints, right? Those two comparisons. We had to compare with the right endpoint of the left list and the left endpoint of the right list. So there was two extra comparisons each step, and that is +2. So this is the relation, the recurrence relation about the complexity of binary search of a list of length n. Now, of course, since I have to divide by 2, this assumes already that the list has length is an even length. So you could replace n over 2 by the floor of n over 2 or the ceiling of n over 2. It really doesn't matter here. Complexity doesn't, that's subtle, small changes do not change the complexity. Or you can just assume, and that's what we're going to do, is that n is even. But remember, you have to repeat this. So, okay, if n is even, let's say 6, then the next problem, you've divided in two subproblems of size 3, but those are not even anymore. So to make sure that everything stays even all the time, we take n to be a power of 2. Okay? And that is not a big problem. If you're going to apply this to a certain list, let's say you have made up a list of size 1,000 numbers, but that's not a power of 2. It's 1024 is a power of 2. Well, add just 24 more elements to it that you know are either smaller or bigger, or you put them somewhere that you know what they are and that they don't never play a role. Okay, so you can always, but it's be padding by zeros. This is called in computer science. This is done all the time. Adding dummies. There's many words of saying the same. It's just to make sure that everything has neatly same size in this problem. If you don't want to deal with ceilings or floors. Okay, so this is the recurrence relation that expresses this divide and conquer strategy, where divide everything in two parts, each of size half. So so we have two parts, each of size n a half of the original size. That's how we divide, and then we put them together by doing two comparisons. Now, so this is recurrence relation, and this is no longer linear, right? The ones that we studied in 8.2. I hope that you see that. That's because it's not depends on n minus 1 or n minus 2. It depends on n divided by 2, which is far, far way back in the sequence. Okay, and therefore it's very hard to solve this. In the textbook they actually give a solution for this particular ones, but I'm gonna ignore all that. We are interested not in the actual solutions but in the complexity. Now remember, complexity, that is this big O, right? So complexity is the big O. I already used here the big O notation, right? It means it doesn't matter for us, 5n and 7n are the same complexity. They are just linear. And 5n squared and 3 and 1000n cube are not the same, not because of the coefficients, because the square is smaller than the cube and stuff like that. Okay. Please, if you don't remember complexity, go back and look at that chapter. Okay, so give another example. Oh, I'm sorry, actually. I realized I made a mistake. I said, yes, sorry. My analysis is actually, I was not smart, because I said we divide it in 2 problems of size 1/2, but we actually only solve one of the problems. Remember, when we were checking where our x is, like either let's look at this particular case, then it's either in the front part or in the back part. And it's only the part it's in that we have to solve. So I'm wrong to say that we have to do twice this thing. We only have to do it once. So this number changes, okay? So let me repeat again. What is this formula expresses? We have a problem of size n. We divide it in 2 problems of size n1/2. These are the 2 problems size n1/2. Then using 2 comparisons is enough for us to say we only have to work in the first part. Or perhaps, if you use a different input, it's the second part. Or perhaps even if there's a very good input, it's none of the parts. So remember, when we talk about complexity, it's always worst case, right? So of course, if we do the search for 7, the algorithm stops almost immediately. But if you have to do a search for 5 or for 13, it might take much longer. Of course, these are small problems. When I say long, I really mean instead of n equals 8, you should think n is 8 million, right? This is the kind of order of magnitude that we really want to talk about, databases of that size. Okay, so we have divided the problem in 2 problems of size n1/2, and only one of those problems, the one that we know that our x is going to be in, after we do the comparison, is either a green one, an orange one, or a blue one. Okay, you want to see an example of this case, x is 13. In the first check, x is 13 comes out there because 13 is bigger than 9. Okay, now 13 is not in the list, I know, but it doesn't matter. At the first step, I think if it's in the list, it must be in the right part. Okay, and if I check for x is 5, it must be in the left part. If I check for x is 7, it's in no part. So in any case, I only have to look at one of the parts, and that is why we have here only a 1 here, and not a 2, which I originally said. That was wrong. Okay, I might have programmed it so that it had to do both sides, but that was not smart of me. Okay, so that's the complexity of binary search. So let me do another example, the complexity of finding max and minima. Finding max and minima. Let's do both at the same time because it doesn't cost anything. So L is now a list of numbers. So A1, A2, A3, AN numbers, and for which we can find the maximum. It doesn't have to be numbers. Actually, again, this problem works for any order relation. If you would have words, you can look at the alphabetic order. Now, of course, this list is not ordered. If the list is ordered, finding maximum is extremely simple. The minimum is the smallest one, the first one, and the maximum is the last one. But the whole point is that this is not a sorted list. Okay, and so if the list is not sorted, what do? Well, it's basically the same thing. We're gonna let's say we have to find the maximum and minimum in this 3, 17, 2, 14, 25, 1, and 19. That's again 8, again, because we're going to keep dividing in 2, so we're going to again want a power of 2 here. So here we have n is 8, which is 2 to the power 3. So how does this work? Well, again, as I said, we divide everything, let's do the black first, the first step, in 2. We cut the list halfway. And then we solve the problem here. So we find the max and minimum here and find the max and minimum in there. So we now have to work with both sides. We apply this, and of course, if we would apply this, what would this be? We know that the minimum here would be 2, so min is 2, and here the max is 17. Okay, and here this would, the output would be min is 1 and max is 20. Okay, so we have solved each of these problems separately. We found the minimum maximum of this problem, we found the minimum problem of the right hand side, but we have to put them together. That's the conquer part. And how do we put them together? Well, to find the actual minimum of the whole list, we compare the two minima, which whatever is smallest. So what's the minimum of the whole list? Well, the smallest of the two, which would be 1 here. And what's the maximum of these two lists? Well, the biggest of these two. Okay, so the biggest of the max is 20. And then the minimum would be the smallest of those two. Okay, so two extra steps to put it back together. So here we could say that f of n, the complexity again, so okay, fn is now the complexity of the max min problem. So fn is again complexity of this problem in terms of the input, where we assume again for simplicity that the input is a power of 2. We don't need to, but it is easier. And again, we could pad this with dummy things or something like that. Okay, comparison, the complexity, not I mean complexity here, right, of this problem is Fn. Well, how does it work? Well, we divide the list in half, of two lists in list of size half. There are 2 of them, right, and in each of them, so what I put here is the size of the list that I'm going to reduce it to after my division. After I divide the problem, have problems of this size. How many? I have 1, 2 problems. We'll see examples where we have more. That's how I divide, but then at the end I have to put things together. I have to do a comparison with the 2 minima and a comparison of the 2 maxima, so another +2 here. Again, we say perhaps +3, +4, does it make a difference? No. Okay, that's just that constant. What matters is that it's a constant, and we'll see other examples. So it's almost the same as the previous one, but okay, we'll see how that affects. And you might be thinking, oh, this is such a minor thing that the complexities must be the same. Let's see. Okay, the next one we saw rather recently, that's the merge sort. And here, of course, is a sorting algorithm, and I already told you it's a very important thing to have sorting, because otherwise the binary search doesn't work. So if you want to apply the binary search, you have to first sort. Right? And if sorting is very expensive, then the binary search is not going to be so helpful to do it. But you'll see we have good sorting, and merge sort is one of them. Now let me remind you how it worked. So we have again a list of numbers. Let's take the list that we had here, right? 3, 17, 2, 14, 25, 1, and 19. What did we do in the merge sort? Again, we divided in 2. Okay, so we split the whole thing in 2, and then we sorted the individual lists. Okay, so assume that we apply now the merge sort to the 2 sublists, and the result of that, so the output will be what? Well, it will be this list ordered, right? The first part ordered, that will be 2, 3, 14, and 17. And the same happens in the left-hand side, 1, 5, 19, 20. Okay, so that's the output after we divide it. And so the question is now, what's the conquering part? How do we put it together? So this is the output of the subroutines, if you want, of the subcall, if from the call to the subroutine. I don't know how to call it exactly. I mean, this is the output when you divide it into each part of each part separately. But now we have to put the 2 parts together. And how do we do that? Well, there was an algorithm called and a procedure called merging, or I forget now what the exact name of that was. And how did it work? Merge list, I think. I think the thing was called merge list. And what did it do? When you have two ordered lists and you have to merge them, what you do is the following. Let's do this here. I use a different color. Okay, where's my color not coming up? Okay, sometimes this. Sorry, when this happens, I have to go in and out. Okay. So let's do it in green. Okay. What is going on with my... Is it, perhaps my pen is slow again? Sorry. So let me already describe what I'm going to do. I'm waiting a little bit for my pen to... my stylus to charge, but I don't think it's that. Okay, so what did we do? Well, we look at each of the two lists and at the first element of these two lists, and we took whatever is the smallest. We know that's going to be the very smallest of the whole, because on the left hand side, let me see what I can get now. Okay, so we compare these two, 2 and 1, and we know that these are the two smallest ones for each of the parts. And therefore, the absolute smallest one will be the first one. So 1 is the smallest one, and therefore I erase 1. Okay? And now I repeat. I have two lists. This list, the left-hand side, and now this list has a new smallest element, 5. I compare those two, and I see that 2 is the smallest. So I put 2, and now I get rid of my 2. The smallest of this becomes now 3. Okay, now I compare 3 and 5. I see 3. Scratch it out. Now I take a look at this 5 and 14. 5. Okay, and then 19 becomes the new smallest guy. Possible smaller. 14. Scratch it out. Comes 17. Compare 17 and 19. I know that is 17. And once a list is empty, I know the rest of the remaining list has to be put at the end. And this is how I merge sort. So let's now analyze the complexity of this problem in the divide and conquer. So again, f of n is, as always, the complexity of this problem. Well, again, I divide in lists of size half the size. Okay, and I'm going to apply my program to that list. So it's the complexity of these smaller programs that I'm now taking into account. How many of those do I have? Well, I have 2, right? Again, I have this half and this half. So 2. So again, we do this twice. But look what happens in the putting together. How many steps did I need in putting this together? If you think about it, I basically had to go for every single element, right? When I wrote this down, well, there's n elements I'm going to have to write down, and these n elements came from n comparisons. Okay, granted, it was not always n, because at the last 2 I didn't really need to compare anymore. But in principle, it could be worst case scenario. I could have to be comparing it until the very last. So I had to do n extra comparisons to put the answers of the sub problems back to the original answer. So I said subroutine. Perhaps the best word is sub problem. I was trying to find that word and I couldn't come up with it. Sub problems. Now you see something else has happened. This is no longer a constant, but it's now a linear term. So it's, if you want, somehow worse, perhaps. And again, we'll see what this actually means. I want to do a few more multiplication, fast multiplication. So let me remind you how we multiply. Okay, if I want to multiply this number with this number, what do? Like the usual multiplication by hand. We put them in whatever order we want. Let's make them both of the same size. Okay, so 2, 2, 1, same. What you do, you take this. You start from the right. You take this element and multiply it with each of the elements over there. So you get 5, 3, and 1. When you're done with that, you take the next element, and now you shift. Right? You start now. You don't write anything here anymore, but you start from writing the numbers here. So 2 times 5 is 10. There's a carryover. That's one thing that happens here. Carryovers. We have to always be a bit careful of that. So that we have a carryover 1 here. Then 2 times 3 is 6 plus 1 is 7. and then no carryovers. 2 times 1 is 2. Okay, and now we do this for this one, but again we start now here. Okay, and so this would be, of course, the same thing, right? 2, 7, 0. So how many steps are these? So this, remember, this both are supposed to have size n. Okay, so here I do, this is n many calculations I had to do here. Another n many calculations for the second digit and n many calculations for the third digit. So in total, these were n square calculations. Correct? And then we even had to put them together, we had to add them, which was perhaps another n square. So you could say perhaps the complexity here, though, is still n square. Okay, we're just adding n numbers, that's not increasing the complexity. So we have okay, give me 1 sec here, sorry. Yeah, okay, sorry. This is not fast multiplication, this is slow multiplication. So what does fast multiplication do? Now, first of all, we have to multiply not in decimal but in binary. So this is about binary numbers. Although it actually works also with ternary or in any decimal system, in any system that you can want to work in, but let's do binary. So we have two numbers, A and B are written in binary. So everything is going to be, when I write down numbers, it's always written in binary. Okay, so let's take an example. So let's say it's 1 1 0 1 0 0 1 1, and this is 1 0 1 1 1 1 0 0, say. Okay, and I have to multiply them. I don't know what these numbers are. I'm not going to really work this out. I'm going to explain the principle. What I'm going to do is, again, as always, it's like seems to be the only trick that we can come up with, but you'll see there are even cases where we do a bit more better or different. I'm going to divide everything in 2 again. So I'm going to make A in a number of half the size, 2 numbers of half the size, and same for B. Okay, and let's call these 2 guys, let's give the names to them. I'm going to call this A1 and this A0, this B1 and this B0. Okay, so A1 is this number, B1 is that number. So what is A then? Let's write down A in terms of A1 and A0. Well, it's A0 plus A1. No, because there are 4 digits. It's actually this number here. If you think of it, what does it mean in A? It means that you have all zeros here, right? Like, okay, if you don't understand this, let's do this with regular digits. Okay, I put in 2 parts. This is A and this is A. This is A1 and this is A0. So A0 is 67, A1 is 13. What is A? It's not 13 plus 77, it is 67 plus 13 times 100, right? Because we have here 2 zeros. In other words, we split this up as 1300 and 67, and that's how we think of this number. So it's A0 plus 2 to the power n A1. N over 2, right? Sorry, n over n over 2. I don't like to do that. So I'm going to say these are of size 2n. So my n is going to be twice the size, twice n is going to be the size of my numbers. It's easier if I do it that way, because then I can write here. Otherwise I have to write fractions here and it gets really ugly. So this is how A looks like, and B is the same, right? B is the first n digits plus the next n digit times 2 to the n. That means the shifting, right? This is exactly what we were doing here. The shifting, this is the shifting that I talked about here. You adding zeros, that's the kind of shifting, that's 2 to the n here, half. Okay. So what is A times B? Well, you can work this out, right? So A times B is A0 plus 2 to the n A1 times b0 plus 2 to the n b1, and that is work out the brackets, distribute a0 b0 plus 2 to the n a0 b1 plus 2 to the n a1 b0 plus 2 to the n plus n 2 to the 2n, right? Sorry, let me get myself a bit space, that's why. So if I multiply these two terms, I have 2 to the n times 2 to the m, that is 2 to the n plus n, that becomes a new exponent, so 2 to the 2n, a1, b1. You okay with that? Okay. So what I could do, and that's not going to work, well, it's going to work, but it's not going to be better, is I can say, okay, right, so let's calculate this, 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 and this. So that would mean I have now 4 times I have to do. So let's see what the complexity of that would be if I would use these guys, multiply them, and then put them together this way. The putting together is 1, 2, 3, 4 steps, or something like that, or perhaps you multiply here still, so it's a little bit more, but again, whether it's 4 or 7 steps, it's just a constant, it doesn't matter that much. So, but oh, see, that's what's happening. My pencil is getting low. So while I'll talk, I have to put it in here. So if I would do this, I would have divided my original problem in half. So I would deal with things of half the size, but I would have to carry it out 4 times. There are 4 products that I have to calculate. Okay, so in the formula, that would be, we would have 4 times the half the size. Okay, so sorry, I'm waiting for my pen to get a little bit of juice. So what I need to say, if I want to do this problem, it would be half the size. Now, okay, the size was 2n, so half the size would be n actually. So f of 2n is f of n, and we would have to do it 4 times, and then we have to put it together, let's say, by 4 calculations. But we can do better. Okay, let me show you how we can do better. This is also equal to, now this is something that I'm copying from the textbook. So this is, if you work this out, you will see that what I'm writing down now is the same expression as before. So this is those of you that love to do algebra check and so on, check that these two are the same. These two expressions are the same expressions. I mean, you have to work out the second one and see their calculations, and eventually it will add up to that. You say, okay, professor, I have no idea why this is better, because this is worse, a formula. It's better. Because let's look at the numbers that we're going to have to multiply. A1, B1. So that is one of the multiplications of half the size. A0, B0, another one. But now look at the middle guy. A1 minus A0, a subtraction is extremely easy, right? So subtractions is something, we don't have to make a whole long thing like this, right? In the subtraction, we my pen is not working. Yeah, we don't have to do, we only subtract once, it's only one line. And so a complexity of subtraction is just n, not n squared. So this to calculate this number is not so hard. To calculate this number not so hard. And now we have 2 numbers again of the same size, half the size of the original problem, that we multiply. So instead of 1, 2, 3, 4, we have 1, 2, 3 multiplications. So we see that f of 2n, the original size, and divide this in problems of size n. How many? Only 3, not 4, but 3. And then we have to put it together. Now the putting together, of course, it's going to be adding numbers, and each of them have size n. As I said, we have to do subtraction here, and of course at the end we have to add. So the complexity is n here. And I realized I might have said it wrong when I did so I wrote here a 4, I should have put here n, right, not 4, because it is 4 additions, but additions of numbers of length n, and those take n steps. I'm sorry about that. So perhaps 4n was the right thing. I made a mistake there. But this is better. So let's say 4n, I don't know exactly what the constant is. It might be 5n, it might be 7n, depending a little bit on how you view what to be done here. So we have to do this subtraction, that's already 2 perhaps, and then we have to, this is nothing. Is this difficult? No, because binary, this is just a binary number with 2 digits, 1 digits, namely at the to end position and at the end position. Okay, so these numbers are very easy. These are just basically all zeros except for 2 ones here, and there's only just 1 1, and so these are very easy numbers. The multiplication with these numbers is easy. Sorry, I should have said that. These are numbers that are hard to, of course these numbers also have the same size, but it's very easy to work with them because how to multiply with 2 to the n. So 2 to the n, let's think of it instead of 2 with 10. 10 to the 3 times 5, 52. How do you do that? Well, you take 52 and add 3 zeros. It's just the shifting. Multiplying with powers of 10 is easy in decimals, so multiplying with 2 to the n is easy. It's just shifting around, it's rewriting. So at most n steps, because of course there are n digits, so you have to write the n digits in a different order, with more zeros. But other than that, the size is still for n. So this is the analysis of this, what we call fast multiplication. Now you say, come on, a 4 and a 3, that makes a difference? Well, that is something for next time. We will see that is true for next time. Very, very quickly, because I will also want to use it. Matrix multiplication. Now, this is something that only really makes sense if you have learned about matrices. So you have a matrix A1, A11, A12, A1, A13, A1n. That's the first row. A matrix is a table of numbers. And for simplicity, we take it to be a square matrix. So it is n square numbers. This is n square. We call it an n by n matrix. So it's a table of numbers. And we can multiply such a matrix with another one. If you have not seen this, you might be a little bit puzzled by the indexes that I'm using here. But if you think about it, so the first index, this 1 here, refers to the first row. And then this, so the next row would, this first index would be a 2. And this, the second index, refers to the column. The first column, second column, nth column. Okay, that's the principle. Now, how do you multiply the two matrices? And this is where it gets a little bit trickier. Let me just show you here. So we have here, say, I'm going to do here, let's say, B1, 5, say, and here would be then B2, 5, all the way up to Bn 5, right? The fifth column, remember the 5 is the index at the end. And suppose I want to multiply it with the third row, so there would be the first index would be a 3 here, right? And then the second index would go through the various columns of that thing. Now, this will give me, what do I do now? I take this row, and let me do a different color, this column, and as I go through the row, I go to the column at the same, so step by step, and I multiply the two numbers. So meaning I multiply this number with that, this number with that, this number with the next one, etc. Of course, this is size n, this has size n, so it all ends nicely at the end. And this will give me the number that is in the third row and the fifth column of the result. So the result is going to be another, so this is the product, I'm multiplying them, is going to be another, so this is an n by n matrix, this is going to be another n by n matrix, and so the result here in the third row and the fifth column, this element is exactly the element that I described to you by taking these elements in this row, multiplying each subsequent one with the same next one in the column, adding them all up, this gives me this element. So let's calculate the complexity of this thing very quickly. Well, I have to do this calculation n squared times, right? Because for each of these, it is an n by n matrix, and I have to do this calculation n squared times. So already n squared multiplications, but each of these steps here, each of these multiplication of this row with this row, how many steps is that? Well, the length of this row, or same, the length of this column, right? In other words, another n. So each of these takes n times, and independently, multiplication problem, I need to do this n squared times, so all in total n cube. So order of magnitude of this complexity of this problem is n cube. Now there exists, but that's very hard to describe. This is a research paper published in about 10 years ago, that you can do this with a divide and conquer strategy. Look at this, 7 times n over 2 plus 15n squared over 4. This is the complexity of that algorithm. I'm just copying this from the textbook they have copied it from the original paper. And in this original paper, this is the complexity of that algorithm. So what they do is they divide the problem into problems. They make these matrices into matrices of half the size. So if we should start by an 8 by 8, it would be now 4 by 4 matrices. How many of them? 7. Which 7? Don't ask me, okay? And these 7, you do the multiplication for these 7 smaller ones, like these smaller blocks. I don't know exactly how it works. Don't ask me. If you want, you can read the paper. It is listed there. And I think the algorithm itself is already much older. It's already almost 50 years old. But the complexity of it was only analyzed more recently. Sorry, read what the textbook says. And so in other words, go back. We have these n by n matrices. We make them half the size, so n over 2 by n over 2. 7 of those, which 7 I don't really know. We multiply those guys. Yes, I know. And then we have to put it together, and that's the cost of putting together. But notice the cost is a square here. So, to entice you to come back for the next lecture, you will see that this is actually a complexity slightly better than this. But to prove this, we need a very important theorem, which we'll call the master theorem of divide and conquer theory. And so, until next time.